Okay, so going back to sound wave propagation and the tuning fork. Remember, it's at equilibrium, a force is put on it, goes maximum displacement, back to equilibrium, maximum displacement the other direction, and finally back to home base equilibrium. One cycle of vibration. As it goes back and forth, it sends out waves of compression and rarefaction. Compression are when the particles are close together, and rarefaction are when they're spread out. And a wave of motion is spread out. The individual air molecules do not move any great distance beyond their equilibrium. They go back and forth around their equilibrium, but a wave of motion is sent out with compression and rarefaction. So there are two events, the rate of vibratory motion of the air particles, or the frequency of the air particles, the vibratory motion, and the rate at which the disturbance is propagated through the medium, the speed of sound. So we have the frequency of vibratory motion and the speed of the sound. The frequency is determined by the sound source. So with the tuning fork, that would be the metal, the length of the bar, the density of the metal, the length of the bar. With a string, it'd be the length, the cross-sectional mass, or the tension. With my vocal folds, right, I have a very high-pitched voice. It's determined by the length of my vocal folds, the mass of my vocal folds, and the tension of my vocal folds. So the frequency of vibration of the air particles is the same as the frequency of the source. It doesn't matter what sound wave results. So if the frequency of a tuning fork is 125 hertz, the air molecules in that medium are going to vibrate with a frequency of 125 hertz. If the frequency of the tuning fork is 250 hertz, the air molecules in that region are going to vibrate with a frequency of 250 hertz. Now, the speed that the sound is propagated on depends on the characteristics of the medium. So waves of 125 hertz and 250 hertz traveling through the same medium are going to travel at the same speed. And what's the medium that we use most often? Air. So air, 331 meters per second. Then there's water. Speed moves about 4 times as fast. And steel, 14 times as fast. So think about when you're on a train platform. Next time you're on a train platform, think, what do you hear first? Do you hear the train coming through the steel rails or through the air? You're going to hear it through the steel rails first because the rails are denser and the speed of sound is faster than in air. So the last thing we need to talk about are types of wave motion. We have transverse wave motion and longitudinal wave motion. Transverse wave motion, the particles move up and down, and the wave moves left to right, outward. So the rope moves up and down. You see A moves up and down, B moves up and down, and a wave of motion is sent out. Longitudinal motion, straight line motion. This is the motion of our air molecules. So the motion of the air molecules is back and forth, and the motion of the sound wave is out in one direction. So it's all straight line motion. You have periods of compression and rarefaction and compression, rarefaction. As the sound wave moves out, the individual air molecules move around their equilibrium. So there's a transfer of energy. During compression, the particles move to the right and back, whereas during rarefaction, they're pulled backwards. Each particle is doing work on the particle in front of it that results in a transfer of energy through the medium. Sound is characterized as propagation of density changes through an elastic medium. Sound is defined as a transfer of energy through the medium. Energy is transferred in a direction that the wave is propagated. The air mass comes across. It creates the resistance, and the kinetic energy eventually gets transferred to thermal energy.